recording. Recording is started. Start screen sharing. Share this entire screen. Beautiful. All right. Hopefully, you'll be able to see that in just a moment. Geez, took its time today. There we are. Awesome. Can everyone see that and that's all right? Dun, 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 dun. Excellent. Fantastic. Nice. Well, yeah, that'll do. Perfect. Okay. Yeah, so welcome to today's session. Lovely to have you all along. We'll be continuing with our machine learning theme that we've been rolling with for the past couple of sessions. But today we're going to, well, first wrap up with what we didn't quite get time to do last time, which is taking a look at an Lstm, and then talking about some of the other things that you can do with TensorFlow once you have your model trained. And then we'll probably go into a section where we talk about how you can compare models to each other and how you can tell, well, this one's better than that one's better than this one, and vice versa. So that will be the goal of today. Before we jump into that, though, we have our normal, super fun admin section, and today is actually bigger than any other day yet. So I'm going to have 3 whole forms. You'll have to forgive me for piling these all up at once. So first one's attendance. That's pretty boring and standard. There it is, posted in both chats. We will tell it us, and then once everyone's filled in the attendance, which is just like your name, that's just how many people come along to these things for funding purposes. We can keep track of how many people or how much money we can squeeze out of people. And then also the second link there, that one is a feedback form for last session. I should have those after every session, and I should always remember to give them during the video calls, and yet I forget. So that's the feedback for last session. It's helpful to hear what you guys thought. I think it might have personally moved slightly quickly, but I don't know if they're recorded, so maybe that's a good thing. Just let me know there. And then finally, a nice exciting one for you all is this last form here, which is, hello friends, are any of you interested in coming to our AGM, which we now have a day for? The day is in the form, so I need to click on the form to remember what day it is. It is Wednesday, the 28th of April at 5:30, so that's right after the bootcamp session. That one will be an hour and a half instead of a 2-hour one. Then we'll just go into this AGM. And during it, you can either run for a position if you're feeling particularly keen, which would be excellent, seeing as all of our committee is probably not going to be at university next year, so we'll need some of you to take over. It's really fun, don't worry, and we'll like a couple months to train everyone. Or if you're not particularly interested in running, but you want to vote for who's on the committee next year, then you can come along to that and vote as well. You don't have to run for anything. Cool, I will give everyone just another second to look at those forms and fill those in, and then I will pull up one more file for myself. Since I have so many of them now. That's the one I want. Cool. Nice. All right. Have I not managed to do what I wanted to do there? No, I have not. That is all right. I'll open that again in a different thing for myself. Not in Spider. That will be too much for me to handle. Wonderful. Okay, cool. All right, I will hope that's a decent amount of time for everyone to fill in the forms. If not, obviously do that whenever, and I'll have a feedback form for this session at the end of this session, as I should at the end of all of them. But without too much more waffling, I reckon we should head on and try making some progress. Cool, okay, that looks good. Nice. So first thing to do is, I guess, remind ourselves of where we were at. So last session, we finished by writing this lovely file here. And it would go through and take our convolutional neural network, which is this one here, and it would train it on our data, which we have, there we are here. You can see our lovely data frame. well, lovely is subjective, I guess, where it has all the EMG data there on one side and then the gesture number on the other side. Of course, that we figured out in the first pre-processing session. Then we went ahead last time and built this model and explained all of these different things here that are called actually hyperparameters. So if you ever hear that. So hyperparameters are like the parameters that adjust the parameters, if that makes sense. So in in any machine learning network, you have the things that are just the parameters. And that's like the bit that it's updating automatically when it's training the network. So the parameters are all the tiny little numbers inside, which... Am I not printing the summary anymore? Nope, I was not printing the summary. Of course I wasn't. So for you model.summary, this is something we saw last time, I think. And then go ahead and run that. Pop. There you are. So it tells you how many parameters are in the model. So those are the ones that it adjusts. The ones that you as a programmer adjust are hyperparameters. And that's what we talked about a lot last time, like these activation layers or the loss functions or the optimizer that we were using. And we chatted briefly about all of those. So, I reckon what we can do, before we head on, is we can take a look at how we would build the LSTM network. That's probably a good place to start, since these were asked about. And I really should have done these in the opposite order, the LSTM first, and then the convolutional one, especially since this one is way more complicated than the one we're about to write together. But I feel like I was half asleep during last session, so that one's on me. Awesome. So we're going to start with a very similar thing to what we had with our last function, where we have an in shape and an out shape, just calling it an LSTM instead of a convolutional neural network. Oh boy, all of these things are tongue twisters. Lots of acronyms in machine learning. Awesome. Do people have any guesses as to where we start if we want to build another model? And remember the only difference between this model and the last model. So we essentially want the same inputs and the same outputs. We just want, instead of the convolutional part, we want to add an LSTM layer, which will do what we discovered LSTMs do last time. And while people are thinking and hopefully putting the answer to what I should type first on the chat, I will whip up our LSTM link so you can take a look at that again. Wow, that is a nasty pile of links and tabs there. Yes, so here's our LSTMs, and it was somewhere down here. Yeah, we see how they function with all the little time inputs, and they'll give us some outputs. But we just want to build a model with things on top of each other like this time. In fact, I will grab this tab, I will extract it, and we will go grab that over here. Wonderful. Any ideas where we should start here? It's probably simpler than you're thinking. I want to do a very similar thing to last time. The crowd goes wild. Suggestions are pouring in so fast, I can't read all of them. Hey, I think that's a good start. Fantastic, yes. So, yeah, when it comes to most of the models you'll be building, if you're just like applying things and not doing machine learning research, you'll probably just be using sequential models. And those are the ones, remember, where you have layers stacked on top of each other. So data goes into one layer and then out and into the next one. It does that instead of any branching stuff or any fancier approaches. So yes, we will do the same as last time and do model sequential and start there. Wonderful. Then the next little bit that we'll be doing, similar to above as well, adding a layer, except this time we want to add a different type of layer. There are a bunch of these built into Keras, which is the part of TensorFlow that has all these. In fact, I'm kind of curious to see all of them. I wonder if it shows me all of them. Let's go on a journey together, because the one that we want is called LSTM, quite logically. I know there's also one for general recurrent unit, which is another one, but I think there are a bunch of them. Yeah, look at that. Bunch of options. So there you are. If machine learning ever seemed too simple, you can go learn about some of those. Yeah, so quite a few ones available. The ones that we are interested in that are relevant to us were the ones we've seen already, but now also one called an LSTM. if it'll bring me there. Well, it sure will eventually. There we are. Yeah, so there's your long short-term memory layer. And then also for lots of these that were first discovered, well, first invented in papers and things, it'll link to them, which is kind of fun. So anyways, that is the one that we're interested in. So in fact, I can show you how to navigate this documentation because that's helpful in the future, isn't it? So if you jump over here, you'll see something like this. You can see it has a whole bunch of options that you can pass to it. However, also, as you'll see, is they all have these little equal signs, which if you'll recall from one of our Python sessions, means that those are default arguments. So if you don't override these arguments, these are the ones that it'll be called with. So you can see by default, it uses that tan-h activation function. That's the one that can be negative and positive, between -1 and +1. A whole bunch of other things here, which is really cool. There's also a second recurrent activation. That's because there are different activation functions here. Here you can see this tan-h, but there's also this output activation. In both of those you can set independently. Here they're both tan-h's. Here they're a tan-h and then sigmoid on the other side. But you can tweak those if you'd like. But yeah, anyways, the important part for us here is the units bit, I think. Units you can think of as how many, or how wide, I guess, the information is going, well, how many bits of information it pumps out the other end. So before, when we were designing our convolutional network, here we did 128. So that's like how many outputs, if you will, that this particular model has. And if we want to, well, sorry, so that's how many outputs that particular layer has, not the whole model, because as you see, it shrinks back down to 8 eventually. But for our LSTM, we could do something very similar, except here, the numbers we might set slightly smaller. Well, we'll try setting them the same to start with, but they tend to be a little bit slower on average than the convolutional neural networks, quite a bit actually. So let's see, we'll start with that, and we'll start with 128, why not? Can't go that poorly, can it? And from there, we'll give it our input shape. You only have to do this for the first layer. Ooh, question, excellent. Does the computer use more models for training or for predictions? Definitely more for training. So training, if you kind of think about it, the way this works, if you recall from, I guess, last session when we talked briefly about how neural networks train and optimize. When you're training something, what's happening is you're predicting values once, and once you've predicted those values once, you're looking at, okay, how wrong are these answers, essentially? So you compare them to what the correct answers are, your correct classifications, your correct predictions. You see how close they are, and then depending on how big that loss is, that's what the loss was. So in our case, our loss is being calculated via this categorical cross-entropy thing. Depending on the size of that loss, you go backwards through your network. That part's called back propagation. That's the bit that involves a little bit of calculus, so you can figure out each one of these parameters. Well, okay, you find the partial derivative of the whole model, essentially, when it comes to one of these parameters. And the partial derivative is essentially just saying, a fancy way of saying, how much will this loss output change if I change one of these parameters? So then you figure out that number, and then from there, once you know that number, you can update this parameter so that it reduces the loss. So you can bump it a little bit to be a slightly larger or slightly smaller number. You do that 32,000 and more times. And then, after you've updated all the parameters, you go ahead and you repeat that process. You make another prediction, how long it is, and you update the parameters. So that's what's happening during training. In prediction, all you have to do is just make the prediction. You just plug in numbers and numbers pop out the other side. So, question, the summarized answer to that question, since I waffled on about it, is predictions are much, much faster than training. Because training has to go backwards and do all of that parameter updating, whereas predictions don't do that. Yes, yeah, essentially that's what they are. Yeah, it ends up being loads of those different, yeah, it's just a single mathematical forward function pass. They're optimized a lot because it does them in groups, and it can do that because some hardware like GPUs can do these things like massively parallel. So if you give it a whole bunch of numbers, it'll pop a whole bunch of those numbers out the other side. Yes. But they're just simple mathematical functions. Awesome. Cool. Happy to help. Good question. Neat. All right. So, yes, we just written this input shape bit down here because that is our first layer. And of course, we're going to do the same as we've done above with in shape, just like that. That's just telling our model how big its first layer should be. And it needs to know that before you can like print the summary of it and things. You can actually get away without adding this if the first thing you're doing is fitting it, because it will just assume that whatever the size of this data is the input size always. But if you give it this information up front, it's kind of easy because then you can do your summary wherever you'd like. And your model's fully built. Cool. Okay. Excellent. That's our entire first layer. Wow, that was a tricky one. And following with the theme of simplicity, probably something again, I should have done the Lstm one first as opposed to the convolutional one. You use the exact same layer from the convolutional network. Because, well, convolutional networks rely pretty heavily, not always, but generally rely pretty heavily on multiple layers. LSTMs can often do things in just one layer. So here, where this one, if you recall, this was finding the spatial patterns of the sensors around the person's arm. So this is finding actual like things in real space because there were 8 different sensors. So this is finding patterns between the 8 sensors. Then this is finding patterns in like a larger time step, and then an even larger time step, and then taking like, whatever its predictions are from the whole thing, just using the biggest, most certain predictions, passing it to this big output layer. And the output layer, of course, was our dense neural network. So if you remember, that was the simple one that we looked at very first thing last week. We've just got a bunch of neurons that are connected to every other neuron in the next kind of layer. And all this does is this will take these 32 outputs. Well, here, actually, you can see it over here. The 32 outputs from the max pooling. It'll perform some very basic calculations on that. And then it will give you 8 outputs in the end. And those are our 8 categories. So like, is it a clenched fist, or is it a rotated wrist, or whatever our other gestures were? In fact, just because we'll be also looking at it later, I'll whip back open that gesture document. Yeah, so there are different gestures where you can clench a fist. The Spider-Man one is, well, perhaps as you might anticipate, like a Spider-Man kind of gesture, or I don't know, maybe a rock-on kind of thing. As you please. Thumb to pinky, finger, thumb to your pinky. And then all the wrist ones, those weren't terribly helpful, but they're mostly described as, well, what they are. The pointer finger was just lifting and dropping a pointer finger, like that. Lovely. Okay. Yep, and recall we're using the softmax activation because what that does is ensures that these outputs come as a probability. It converts, whatever these random numbers coming out of the thing are so that they all sum up to exactly 1. It's a probability distribution of which one is most likely to be, which gesture it's most likely to be. And then we finish with, again, exactly the same thing as before. Optimize the model with the same optimizer, using the same metric, and the same loss function. Just like that. Yeah, definitely should have done that one first last time. Cool. Then we just return our model, just like before. And because we've designed this function with the same input arguments and the same output return value, we can do something very nice and easy. So I'll get rid of this summary. I'll put the summary right before the evaluate. I feel like that would be useful, even if it might make TensorFlow clean. Let's find out. Boom, 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 boom. Beautiful. Okay, nice. So that works well. So our final result is first, because I haven't changed it yet, is convolutional neural network. That one has 32,000 something parameters and is 96.5% accurate on the final thing. So I'll just actually take that and copy that, put it in our file here. Obviously, you can't just have random non-Python code here, so you have to comment it out. Fun shortcut for that in Spider is Control-1. There you are. And so that's just so we can save that and look at that again in a second. And now what we'll do is take our convolutional neural network, change to building in Lstm, and give it another go. Name is not defined. Of course it isn't, Brooks, because I haven't imported it. So remember earlier we went and looked at the documentation for keras.layers or tensorflow.keras.layers. So all we need to do up here is just add it to our list of layers that we are importing. I'll put it here, Lstm. Lovely. All right, there we are. We're training. Off to the races. Aha! Okay, so we have a result back in the end. Okay, so you can see here, just like last time, we got our little, output from our machine learning model. Well, the shape of it anyways, like the whole structure. That's the word I was looking for. Goodness. You have your Lstm as the first layer. Each one of those is outputting, well, at the end, it's outputting 128 little numbers that summarize what's happened. The dense then categorizes that into the 8 categories, and we get something out the other end. So you'll notice a couple of things about this. If I paste it in, let's see, where did I included the model thing last time. I don't need to this time. Copy raw text. Go and we'll put it up here. Why not? That was the least efficient way to do that. Wonderful. Cool. Okay, so you can see, if we're looking at these two, you can already see a little bit of a difference in a couple of places. First of all, this has way more trainable parameters. So that means there's a lot more numbers that it has to update when it's going through and training things. And you can see that most of those are coming here from our Lstm layer, as well as some of them also coming from the dense layer, but not as many. Although there are more than our last other dense layer. That is because here you need to take 128 things and turn them into 8. Here you're taking only 32 things and turning them into 8. So I believe, actually, the way that those are calculated, because every one of those output neurons, because it's a dense neural network, is connected to every one of the inputs. So I think, actually, that would be, well, if you did 8 times 32, almost. So it seems like it's slightly fewer than if it was every connection. Okay, fair enough. Nice. Okay. Okay, no, sorry, yeah, of course. It's every connection, but it's also plus the biases, isn't it? And that will be 8 more biases, so that's how that works. So that's how that number is calculated. Yeah, there we are. So you can see, obviously, if you have a larger number of inputs, say 128 instead of 32, then you're going to have a larger number of parameters. Yes, okay, that matches up. Okay, that makes much more sense. Cool. So that comparison between the two parameters, I guess. So this one up here is about double the size-ish, well, actually a bit more than double the size of our convolutional neural network. And I don't know if you noticed, but when we were training it, you can also kind of tell when we're training it, it's moving slower. So you can see here, you can kind of almost like, well, obviously it takes a second. If we change it back to the convolutional neural network, this one, I reckon, will finish before I can finish waffling on about it, if we just go ahead and smack that, and then yeah, it's done. So that's one of the consequences of perhaps having a lot of these parameters. Also, generally speaking, since this is what's called a recurrent neural network, LSTMs, remember recurrent ones are ones with little loops in them, like that, where you go back and the output of it gets fed back to it as input in the next time step. That essentially means you need to process the time steps one at a time. That can sometimes slow down the processing of things. Whereas our convolutional neural network can even look at like several time steps at a time, and convolution is a really efficient process because you're just kind of taking a mask of numbers and multiplying it by another set of them. So that's really fast. So generally, convolutional networks are faster to train. And then finally, and perhaps most annoyingly, since we put on, well, I guess it wasn't that much effort to write this LSTM thing, but since we did put in the effort to like write the LSTM thing, the accuracy is also worse than our convolutional neural network. So it kind of just looks like it's worse in every way. And while that's not always true, well, there are definitely problems that are easier to solve with LSTMs than convolutional neural networks, especially lots of things to do with time, like this problem kind of is. This is not one of them. We originally used an LSTM, and I think it was after me and Thomas had like finished all of what we were doing for the summer, and I was thinking about like writing up some blog posts about this, which I've technically written 2 of now, but only posted 1 of. I discovered that our LSTM we'd been using was just worse in every possible way compared to the convolutional neural network. So that's why we ended up using this one instead. It is a smaller model with fewer parameters, so it's easier to store. It is a faster training model. You can see 23 milliseconds per step versus 4, and it's also more accurate in the end, which is nice. Although, it is worth saying that accuracy can be improved by training this model more. So we'll do that just for giggles while I'm talking about something else, I guess. Epochs, if we train it for, say, I think I had 100 at some point, not 1,000. We'll be here all day. So now, again, just as like a time comparison, here's a convolutional neural network for 100 epochs. So that's like pretty quick. Long enough I had to wait for it for a second or so, but that trains real fast. This Lstm will take longer, so I'll start talking about other things while it's running, and then we'll get to it, and it should be more accurate in the end. That is another thing that we could do. That is true. The only thing about LSTMs is it doesn't make a whole bunch of sense, I guess, to add layers to them directly. Because if you think about it, they're kind of just outputting one thing after going through in time. So you could definitely add more layers. It's not as easy to do or necessarily as common, I guess. You could add different types of layers. That's certainly something you could do. But I don't think it's too terribly often done, because essentially out of this thing in the end, since the network does look like this, down here is just an easier way to look at it. That's like an unrolled way. But the way that the network essentially operates is this looped fashion. So you could put these in several layers, but I think that would just double our parameter numbers without doing too much. Well, you can't stack. You could add other layers to it, but you can't stack the LSTMs because they have a very particular input shape that they require. They require the data to be in the form that we've prepared it in, which is, if we look at our EMG tensor, as this size here, so that's the number of repeats. That can be any shape, but then it requires the next dimension to be the time dimension and the last dimension to be the feature dimension, which is our sensor things. So here you can see the output is now 2-dimensional instead of 3, so we can't put another LSTM directly on top of that. You could layer dense things and probably get a better performance. You are correct in that case, yes. Although I'll admit I haven't experimented with that yet, but hopefully after today you'll have all the tools you need to experiment with that yourself and let me know how it goes, because that would be interesting to see. Awesome. Does that answer that question? Sorry, that was again very waffly. Well, that is certainly something you could do. No, I think you might struggle with that actually as well because of the dimensionality as well. You could put a convolutional network before the LSTM probably, because this will output, see here, still in 3 dimensions, where that's the time steps, that's the number of features. This current model, though, you can't put the convolutional after the LSTM because you wouldn't have anything to travel over, I guess, if you think about it, because remember the convolution is like a sliding window, but there is no time dimension to slide over here necessarily, so this would just be, well, a single point that's 128 deep, I guess, if you're thinking about it from the convolutional perspective. But we can certainly try to do it the other way around. That would be kind of actually interesting. Those are good questions. Thank you for asking them. Yeah, lovely. Just because I'm kind of curious and because you've sparked me to do this, I will do that, and we'll see how that goes and see if it gives us something worse or better. Although I'll need to reduce that back down to, say, 15 just to make it even. Yeah, that'll give us a better difference. So we can see, though, before I wipe this all away by running that model, after we ran this thing for 100 epochs, which definitely took longer, it's much better in terms of accuracy. We're up to 95% nearly now. So you can see this LSTM can get very, very close to the performance of the convolutional neural network. That's what we found the first time we tested it as well. It's just that it takes longer to do so. And we'll take a look at, later in the session, how you can actually graph the training progress. So you can tell when a model is just about fully trained and when it has longer to go. So that way you know not to set the epochs number too low or too high. That's a really helpful thing to do. Cool. Thinking about this conceptually, yep, that makes sense because this first one is going to get us the pattern on those 8 different things. Then we're going to feed that into the LSTM. This is going to be an obscene number of parameters. That's probably going to take ages, but we'll see what happens. Okay. Cool. I think that won't crash. Let's find out together. Da-na-na-na-na. Yeah, okay, so that's about twice as slow, or maybe... yeah, it's definitely slower than our original one. The accuracy is marginally better. I'll admit, it's a bit tricky to tell if that's just random chance or if that's a genuine improvement. So what we will do, since the whole point of today's session is to figure out what's random chance and what's genuine improvement, I will make that its own little thing, as you suggested, both of them together, and I'll create a copy for the other game, and we'll compare all three of them once we have the tools to do so, which should be very soon in this session. So, a very fun idea this is. I'm glad we have some fresh ideas coming out. Fantastic. Okay. So, yeah, I think that's probably all I'll say about LSTMs, actually, for the time being. We'll come back to that once we're evaluating the different models. Do people have any questions? I will ask, and I will also do a poll in the Discord, since Discord's been very poll-less today. How are people using 8 LSTMs? There we are. Is the poll bot going to swoop in and do a reaction to that? Or have I done the poll incorrectly? Pollbot is on its day off, it appears. Hey! Well, okay. I'll take that. Yes, lovely. Okay. I'll also add well, okay. If there's a thumbs down, I'm sure we'll add one just in case. I've added a thumbs down so people can click it if they're not feeling great. Wonderful. Okay. Nice. Yes, I think that's about all for LSTMs in general. We have now 3 models that we can compare with today's stuff that we learn. Before we jump onto that, we'll also jump on to the couple little things that I wanted to finish up last session. So I think really briefly, if I recall, we saw how to get predictions out of a model. So it's worth giving that a look, I think. Yeah, yes, that's the bit that I added, and I removed it all because I did some crazy stuff in it. Okay. Spider, why do you have to do this to me? Okay, there we are. So up here, then, now that we've printed out accuracy and stuff of our models, I'll change this back to the CNN. Well, actually, you know what? I'll keep that as the LSTM. That'll give us some more interesting answers here. I have broken something. Don't exactly know how I've done that, actually. Error in user code. I swear I've not changed anything unless I've done something very silly. Cool. Okay. Well, I'll ignore that for now. Can I? Let's see. Let's close that and restart that. Something is missing in LSTM. That is very true, and that's entirely my fault. Good catch. Of course, since this is now our first layer, we need to give it an input layer. You can see now why I think it's called input shape, isn't it? Yep. You can see now why I made a point of adding these here instead of later, because despite the fact that TensorFlow should sometimes work with things that way when you fit them first, sometimes it gives you something like that. And I don't know about you, but input B is not mat mul op has type float 32 does not match that other type. Well, that doesn't say to me you've forgotten your input shape. I still actually don't know where that error comes from, but I have run into that before. That is the solution. Very good catch. We need to give it the input shape here. So if your TensorFlow is being squirrely, maybe be explicit about the shapes of things, and it will be less squirrely, hopefully. Wow, look at that. Got all of the things right in training. Accuracy of 100%. Well done, Mr. Model. I assume that's random chance, but sometimes you get lucky. Okay, cool. Thanks for that tip on fixing that. And now we can get on to predicting some things. Yeah, okay, that's back to more expecting. Looks like it's overfitting. Entirely possible. Well, we can find that out today as well. Yeah, although this data here, when it's evaluating, that is on the testing data. So that is theoretically data it's never seen before. So that should be somewhat dodging the overfitting, or at least that performance would go down if we were overfitting, which is something that we should be able to find in our graphs today. But yes, that is indeed an issue that sometimes pops up. Cool. So just as you can evaluate our model with model.evaluate, predictably, haha, that was a pun, you can predict things with the model by doing model.predict. So we could predict all of our values. I think we should predict only a small slice of them, so that way we can look at them more easily. So I want to predict the first 4. I remember this is 4 because 0 is included at the beginning implicitly. Just kidding. This is going to be 3 because it excludes the third one anyway. So that's going to give us 3 things and predict which class that they belong to. So if we go ahead and do, in fact, I'll do this over here so we can see it. Dun, dun, dun. Et voila! You get something horrendous. So this scientific notation display is really, really helpful sometimes. And other times, I really don't want to see it. For when you don't want to see it, you can turn it off. And you can do that with... Don't worry, I had to Google this one because it's pretty niche. That is Numpy, and if you set the print options for Numpy to suppress something, I think it's just suppress the special printing that Numpy tries to do, to true, then it won't do the scientific notation. So actually, if we go ahead and import Numpy, Numpy as NP, it's our standard import for Numpy. I don't really want to run that whole thing, but I will. There's really no point in doing that, actually. It's alright, I could have just done that. Okay, it trains, lovely. Wow, look how accurate it is today. And I can do the predictions, and there you are. Now you can see their real numbers again. Cool, so you can see, for example, this first data point that it's predicting on, which is the first thing of our testing data. So actually, if I take a look at what that should be, we can take a look at A or Y test even. So that's all of our correct categories. There we are. So that's what things should be if they were perfect. So you can see this first one, it's not that, so it's got a low probability, that's good. Second one, low probability, that's good. Third one, low probability, that's good. This one is the correct answer, gesture 3, if we're starting at 0, so gesture 0, 1, 2, 3. This one has a pretty high probability. It's an 83% chance it's that one, which is super nice. And then you can see the rest of the below. So that first one, it's got correct. The second one should be one more over. That one's gotten correct with a 93% chance. And this last one should be the exact same. And there you are with an 88% chance. So our model's done very well, as indicated by its high accuracy on the training data this time. Yeah, I guess you're right. There could be some weird overfitting. Yeah, definitely possible. In fact, I'd probably tend towards overfitting being a possibility with that many parameters. But yes, so here you can see our probability distributions are predicting, if you pick the biggest one of those numbers, they're predicting correctly the correct answers, which we can see here. If we want to combine these two things and look at them simultaneously a little bit more easily, there's a way to do that. That's the sneaky thing that I pasted, I think, in last time around. So we'll do print, because I want to print them directly from here now. Well, I'll show it over here first. Numpy, you can stack arrays in different dimensions. So if you just do Numpy stack itself like that, I think we actually saw that in our pre-processing thing. That will take a list of Numpy arrays and turn them into a Numpy array of Numpy arrays. But there are other ways you can put things together as well. So for example, if I do dstack, that adds a new dimension. So it's like depth stack almost, I guess. And I want to put our predictions in one of the two new layer things, and then in the second one, our correct answers. This might give me grief and might not work. What is going on with brackets there? Bad things. That might complain. Yeah, that's kind of what I thought. So you have to give it one argument, because it's essentially taking some like collection in Python. So it's like a list, or in this case, a tuple, because I put brackets around it, so that's just a tuple. And then it will take those two and combine them into one Numpy array, this time stacking them depth-wise. And what that means for us visually is we still have, here's the first one, here's the second one, here's the third one. Then you have categories as this other dimension, which is the down dimension, so here are y. And our, well, depth kind of ish, if you will, is the left and right part. So here you can see it just lines up on the left. This is the probability that our model predicted. This is what the correct answer was. You can see here, the correct answer is lined up with the 83%. Here it's lined up with a 95, and here it's lined up with the 88%. So we'll go ahead and grab that code there and dump it in a print statement in our file. Print. Beautiful. So now, when we train our model, it'll probably do, well, maybe not as well, or maybe really well this time. Guess we'll find out. It'll spit out some answers for us. Lovely. So this one looks like it's gotten correct again, gotten that one correct again, and this one has also gotten correct. 72% chance. Lovely. Yeah, really well done, model. Going fast. Cool. All right. So with that out of the way, that's how you can make predictions with the predict function, or method even. And then you can, out the other end of it, put it next to, I guess, our correct testing data, so you can look at individual data points if you're curious, which is what we've done here. And I guess there's one more cool thing to show before we move on to like the evaluation content, I guess, that we planned for today. And that is, you can save and load these models. So say you did take a lot of time to train this. Say your computer is, I guess, either a little bit slower, or you set it up for way more epochs, or it's a much more complicated model. You don't want to lose it. You'd like to save it somewhere. Well, luckily, there's a way for you to do that. So you only have to train these things once, even if you're moving them to like a different computer. And then you can just reapply them everywhere. So the way to do that is, now I know this is going to shock you all, probably didn't see this one coming, model.save. Good thing that Python's very straightforward about these things. Then you give it a file name that you want it to be in. So in fact, I'll take where we've already saved it. Whoops, spoiler alert. EMG model. And I will destroy that folder. Goodbye, my friend. I hope that wasn't important. That's all right. Everything's Git version controlled. I can get it back if I delete something important. Just another plug for Git version control. And then here you just give it the name of the folder you wanted to save in. So we'll call it EMG model, because that's the one I just deleted that I want to store it in. Go ahead and run this. It does all of its training. And then once it's done doing the training, it will pop up. Dun, 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 dun. There you are. It's done its whole saving thing. And et voila, the EMG model is back. Full of a bunch of things. You've got your Keras metadata, saved model metadata, assets that are none, doesn't look like variables. You got all your variables there. So very exciting. Now that folder itself, I'm sure you could, if you were clever and dedicated, able to load that on your own. However, it'd be a little bit silly because, luckily, TensorFlow, as well as giving us a way to save models, gives us a way to load them. So, if we want to load them, then how do we do that? So, here we actually don't use a method because theoretically you won't have a model yet. Well, actually, just for the sake of showing it off, let's see if we can get this to work. So, Variable Explorer. Why is there not a model there? That's a good question. Well, model doesn't want to appear in Variable Explorer, but that's fine. You can trust me there's a model there, because if I type model, it tells me it's a TensorFlow sequential model. We can destroy it. Goodbye, friend. With the delete keyword. So del, that'll delete an object. That's lots of objects in Python, so you can delete lists like that, or vectors, or, well, lists and vectors are basically the same. Lists or dictionaries, things like that. Cool, I will jump to that question in just a moment. So we delete it, you can see the model has disappeared. Lovely. Okay. To ping pong to the question. Silly question, but what are those numbers in the first column of the stack matrix? Don't worry, that is not a silly question. These numbers here, those are the 8 outputs of our neural network. So those are coming directly from this dense layer. Those are the numbers that this dense layer outputs after, of course, they've been put through the softmax function. So this is the output from neuron 1, output from neuron 2, neuron 3, 4, 5, 6, 7, and 8. And they are essentially a probability distribution that is telling us which one of these categories it most likely is. So it's saying there's an 81% chance that it's this category, and it's correct because it definitely is this category. Same here, it's an 85% chance. Here it will be 74% chance. So it's just like how certain the model is, I guess. Yeah, awesome. Yeah, and the only reason that those are a probability distribution, though, is because we put them through the softmax activation function. Without that, they're just arbitrary numbers that don't have like any units. This will make them a probability, which is nice. And, well, okay. Just to promise to you that they're a probability distribution, they all sum to 1. So if I grab model predict, well, I've missed a bracket there, but that's all right. Who needs brackets? That's funny. I just finished deleting my model, so I can't call it. That's all right. We'll load the model, and then I'll show that off. So first, let's load the model. We do that with a function called, unsurprisingly, load model. However, this function, as you might see from Spider's little hint, it's undefined. How do we get that? Well, we can just jump up to our imports. As with everything in Python, it belongs, or it comes from somewhere. So here from Keras models, so that says both the types of models, but it also has ways for loading models. So you can import the load model function from Keras or TensorFlow.keras.models. Excellent. And when you load the model, it is pretty easy. You just give it the same name that you gave it before. So in this case, it's going to be PMG model. And then you save that in some sort of variable. So I'll say reloaded model equals. And then over here, I'll just do model equals since I want that back. So go ahead and load that. It's fine because I haven't run that import yet. That's fine. I will run this import. There we are. So you can see it takes a second to load, but like that's nowhere near as long as it would like take to train. So that it loaded the whole model in the time it took for that to return, which is really nice, and it's fully trained because that's where we saved it at after it was trained. So now if we go ahead and run my predict thing here, we'll get back out, well, some complaints from TensorFlow. That's just because it's not happy, I guess, in the order I've been calling the functions. That's just like a performance thing, but it doesn't actually call any issues. If you call it again, it goes away. Here you can see same numbers as before. We have our 81%, our 85%, and our 74. And just to promise you all, don't worry, they're a probability distribution that sums to 1, because 1 is something certain to happen, and it's certain to be one of these things. If I take that, paste it into sum, which just finds the sum of a whole bunch of numbers, like that. Wow, just about 1. The weird decimal way down here, remember, is because floating points are kind of inexact and get a bit squirrely. So yeah, that's where that extra bit of stuff comes from. It's just some imprecision. Sometimes that number will be less than 1 or greater than 1, but always by a very, very, very tiny amount. Cool. Okay. That's saving models and loading models. Fantastic. Okay, I guess I'll ask if there are any questions about both the predicting things and also the saving and loading models. So any questions? If so, go ahead and let me know. We'll see if Pollbot wants to wake up. I'm going to double check how I do polls. That's because I wrote the poll wrong. It's entirely my fault. Feeling about saving and loading models and predicting. Forgot to include that. Cool. There's the poll. Maybe. Oh, I've done that one wrong as well. Goodness. This Pollbot is incredibly picky. It used to just take a colon. Now it just takes a plus, and it won't accept it if you give it a colon. There you are. Sorry for the faff. Okay. Lovely. Seems like people are feeling okay so far. Nice. Okay. Cool. With that out of the way, if you do have any questions, of course, feel free to type them in either of the chats at any point, and I will get to them. But aside from that, I think it's time to move on to what we were going to do today with our new content, I guess, if you will. Let's start by thinking, I guess, about some information that it's useful to have when you're trying to evaluate neural networks. We could, for example, if we wanted to, say our network is kind of doing poorly, it's getting like a 60% accuracy or something, even after we've tried a whole bunch of things. We want to find out what it's mixing up, which parts it's wrong about. Well, an accuracy percentage tells us overall it's missed some number of them. We could look at exact things with model predict. In fact, I could predict all of the things at once. Oh my goodness, what have I done there? Oh, why are you so mean to me, Python? I just want to go to model predict. There we are. We predict everything in the model by just giving raw data. Wow. Look through all of that by hand and find out which things are mismatching and then check which category they belong to. But that doesn't look like fun. So luckily, there's a very nice way to look at these sorts of things. That's called a confusion matrix. So we'll see what that is in just a moment. In the meantime, let's go ahead and write ourselves a nice new function for evaluating how well our model has done. And this will give us both the accuracy percentage that we've already got. It also shows a confusion matrix for some arbitrary data. So we'll call it evaluate. And here we'll give it our model, some x data, and some y data. Yeah, okay. I'll try and use machine learning terminology here. X data you can think of as, well, no, so it's not even really the same machine learning. That would be like inputs, this would be like labels. We'll keep it as x and y data. Point is, that's the part that you put into your model. This is the bit that comes out of your model. That's the idea there. So nice. First thing we want to do is make some predictions. So remember a second ago when I made all these predictions, we're going to do that, except now store that in a variable, because we'll be needing that in just a second. So we'll do model.predict here, and we're going to predict from the x data. That's the idea. Lovely. Cool. And now we're going to run that, or load that in even. Am I sick of that constantly retraining? A little bit, actually. It's saving. Yeah, it takes way too long for me to be happy with. So, goodbye, my friend. You are a comment now. Nice. Okay. So now I can run things, and this is just with the data from our last runs. So I can do, like, evaluate our model. And we can do it with our X testing and training data. Well, this actually won't do anything, will it? It'll print us something, I guess. Maybe, actually. I'm not entirely sure if it does. I want to type train, even. Y train and X train. Cool. Yeah, okay, so that doesn't print anything yet. Which makes sense, because we're not printing it. This is storing it in a variable. If we did want to take a look at it, we could return it. That's probably the wise way to do that. Return. Run that nice and fast. There we are. So there's our output. That's things predicted. But really what we want to do is compare those predicted outputs to the correct outputs and see where they line up. So we can do that with a confusion matrix. So we'll import a nice little tool that'll help us get to this confusion matrix. TensorFlow has a version of this, but it's not quite as actually well fleshed out as the one by scikit-learn. So we're going to use scikit-learn's version. So from scikit-learn, we want to import. I don't actually know what part that's in, so let me check real quick. That is in metrics, so scikit-learn metrics. So metrics are like a way of evaluating, I guess, the performance of your model, which is kind of what today is all about. So there are our metrics. We imported them. Well, we can import them. We want to import the confusion matrix. There we are. Excellent. Are you angry? That's fine. I don't mind if you're angry. I've commented on a whole bunch of my code. Deal with it, buddy. Okay, cool. So let's run that. What we're going to do here now is restore this to storing it in a variable. So y predictions or predicted. And now, instead of returning what we returned before, we want to return our confusion matrix. So we call the function. It's well, you start with just confusion matrix, named as it is. You give it both the predicted data, so the data that you got from your model, and you also give it the correct data, which is the data or the labels that you know are correct. So that's our ypred, or that's a good point actually. I should. Yes, of course, yeah, sorry. So this y data that we're giving this function, since we're evaluating it, that is the correct already, yeah, which is fine. So we want to compare this y data to the predicted y. And we will do that here. Although we'll run into a bit of an issue. So actually, before we do that, we want to be building this confusion matrix, just I guess to briefly explain what they are, so you'll know when you see it in a second, is they take a list of like categorizations. So you have 5 different categories. It'll build a 5 by 5 square, and it will tell you where your predictions line up with your data, and it will tell you where your predictions are confused for some other, correct label. So first what we need to do actually is convert these into gesture numbers. So earlier, well, we started obviously with things as gesture numbers, but we need to get back to that from this whole form here. So for example, I guess something we'll just use one of these. So this one up here at the very top, is that a decent example? Oh, well, no, it's not, because it doesn't give me anything. That's right. If I evaluate and then grab the first thing from that array, there we are. There are some numbers to play with. So in this case, it is predicting with an 80% chance that it'll be this one here. So that is the 0, 1, 2, 3, 4th gesture. Now, of course, we could write our own code that loops through this array, and it will check for where the biggest one was and then return that number. But luckily, that has already been done for us in the form of a function called Argmax, which won't be imported, but I'll type anyways there. Yep. Okay, so that's not imported by default. But what Argmax is, as you'll see in just a moment, and we will need to get it from Numpy, actually. So actually, it's already in Numpy, so we can just do what we've been doing with everything else that's in Numpy and just do np dot. So if I do np.argmax, give it our list, et voila, well, I messed that up. Et voila, it gives us 4. So what's this argmax function doing? Well, it's doing basically what I just described. It will go through a list, and it will tell you, and it doesn't have to be a list actually, it can be like a matrix even. Yeah, that's as many dimensions as you like. It will go through, and then it will calculate, aha, this is the position of the largest thing in here. I will use that as my argmax value. So it's giving you the index of the maximum value. So index 0, 1, 2, 3, 4, and that's there. This also works, like I hinted at a second ago, on two-dimensional data. So let's just see what happens if we just add, well, not even really a second row, but pretend it's two-dimensional by adding an extra layer of nesting around it. It won't work if I do that there. I'll try and make that look a bit nicer. There we are. It'll also give us 4, which is nice and helpful, I guess. Let's see if that behaves quite as nicely if we run it on our prediction file, or prediction output. So here we are, evaluate. Remember, actually, before I do that, this just gives us a dumping of all the different predictions currently. This is before, it's not matching this code anymore. I haven't loaded this code yet, so it's just dumping all these predictions still. All those predictions, let's use argmax on it, so we can get which categories they belong to. But uh-oh, that's not what we were looking for, is it? That's not possible. So what it's doing here is it's not, in fact, giving us well, okay, so we can take a look at the shape of evaluate even, actually, and that'll help us elucidate this. Shape. There we are. So here, it's not looking at just the maximum index on the, I guess, x direction, you can call it here, and our little direction of 8, but it's also looking in the other direction. So this is going through, and that's why this number is bigger than both of these numbers, is because it's not the first value, the second value, third, fourth, fifth, sixth, or, I guess actually this would be the 8th value, or the 9th. And so it's going on and it's counting all these values in both dimensions, but we don't want that. We just want it in one dimension, so it gives us a multi-dimensional output. Luckily, there is a way to do that. Get another optional parameter. You say axis, and you give it different axes to work on. So we'll start with 0. Then you can see we have that, which is probably not what we were expecting, because that's along the wrong axis. But what this is doing is it's going down this data this way, and it's picking for each one of these 8 positions, which one has the largest thing for it. So for example, this is essentially what this is doing is telling us the most certain result about gesture 0 is in line, or is the 75th one. Most certain result for, I guess, what would that be? Gesture 4 or gesture 3, if we're starting from 0, would be in the 156th or 154th like row down. So let's try it on a different axis. That's not that one. There we go. This one there. Aha, okay. Maybe that's better. So this is giving us a list of numbers here. In fact, this list of numbers should be 173 long, I hope. Yep. So that's actually going through this other dimension here, going through all 173 and finding the maximum value in each of these prediction outputs. So this one is the one that's actually converting to gesture number. And we can sanity check that by taking a look at our first 3 as we have done before. Okay, I thought it was much closer. There it is. So our first one, biggest number is here. That is the third value, even. Is that what I expected? That is not what I expected, because that's giving me 4. Ooh, I wonder if that's starting from... Yes, of course, because there are no zeros. Oh, there are some zeros. Very odd. Oh, sorry. Of course, because I've rerun this predict, and I think that's giving us something maybe different than evaluate. I don't actually know if that's true. Let's find out together. Let's just use evaluate and get some things from it. Oops, of course, it's still in the Argmax. I don't want that. Lovely. There we are. Okay. Yes, that makes more sense. Yes, okay, much better. So these are the numbers we were used to seeing before. So 0, no, 1, no, 2, no, 3, no, 4. Yes, that's a big number. It's 83%. So that's where 4 comes from. Then our next 2 should be not this number, but the one right after it, because it's 5. And if we take a look, yep, 92% and 60%, which, while it's a bit low, is the highest out of any of these, even though this one's up at like 18%. So that's how Argmax works. We can go through and get, essentially simplify down our probability distributions into just getting the biggest value out of all of them. And that's going to give us these categories. So then we can just say, okay, here are the predicted answers, if you will. These are the labels, the gestures that we're predicting. And we're going to compare those to the correctly predicted gestures, which is what is going to be in Y data. Well, almost in Y data. We'll also have to run the same thing on Y data, because if we take a look at, well, like Y test is our testing data. Take a look at this, you can see it's very nice where it's all, zeros and one of them just has a 1 in it. So you can be pretty certain about like which one it is. However, with that being said, it's not a single number. You still have to look through and find the biggest one. Luckily, our thing we can apply just as easily to that. So we can just do. That's why. I've discovered my, yes, Y test. Lovely, just like that. Pop, outcomes, and answer. By the way, in case you were curious, a second ago, when I was like, why don't those numbers match? That's because I was running through here the training data, not the testing data, because I am a silly boy. So that's why these first 3 numbers didn't match the first 3 that I got when I just looked at Y test, or Y test, or X test and Y test. Cool. Okay. Awesome. So I'll go ahead and write that in a little line down here. Yeah, it's fine. Actually, we'll put that in our evaluate function. That's the point, isn't it? Okay. So what we're going to do is return a confusion matrix. What the confusion matrix takes as its first argument is the predicted results. So here in the predicted bit, we're going to have to use our Numpy Argmax. So this. However, we're not doing it on the X test data. We're doing it on these Y predictions. So go ahead and do Y prediction. Lovely. Cool. And then if for our second one, we go ahead and pop in the same thing, but this time for our correct answers, we just do Y data, because those are our correct things that we're pushing in here, or our labels even. Wonderful, and now we can take a look at what a confusion matrix looks like. Just kidding, we cannot, as I have not run the evaluation function. There we are, et voila. We get something that looks a bit like that. I've run that with the training data, so of course it's 100% accurate there. And the way you can tell that is because everything is sitting on this diagonal line. So what each one of these rows and columns is, or other way around even, rows and columns, each one of those represents I believe this direction is the predicted gesture, and this direction is the correct gesture classification. So for each gesture that belongs to class 1, 22 of them are predicted to be part of class 1. And for each gesture that belongs to class, or I guess that would be 0, sorry. So each one that belongs to class 1 here, 22 of those have been predicted correctly. They came from class 1, and they were predicted to be from class 1. But over here you have 1, so this one here means that one of these was misclassified. So something that should have been, say, I guess if this is the one it should have been, so it should have been gesture 1. Instead, the model said, I don't know, this looks like gesture 3 to me, and I got that one wrong. So a second ago when I said it was 100% accurate, this one's actually not quite. This is almost 100% accurate on the testing data, or training data even. Yeah, okay, cool. So that's what that little 1 means. It's off the diagonal, so that's one of the errors. Now you can look at this, and that's like, fine. You can certainly get stuff out of this. You can do operations with this sort of confusion matrix. And because our functions doesn't care about the data we put in, we could change it to the testing data, which is probably a better picture of things, actually. So testing data, there you are. You see that's a bit more divided. For example, this gesture is getting mixed up a decent amount with the first 2 are getting mixed up, I guess, is what it's saying here, because 8 and 3 are both overlapping. More confusion here. And you can see this one's in general much less perfect than the last one. But a nicer way to look at this would be graphically. So luckily, scikit-learn also has our back there. So we can take this lovely confusion matrix that we have calculated, and if we go here and plop in some answers, or store that in a place rather, so there we are. Confusion matrix, we'll create a new variable for it. Next thing we want to do is actually display it. So again, from scikit-learn, there's something here called, well, it's an object even this time, or a class, I guess. Confusion object, or confusion matrix display, that's the one. So the reason we have to import this, which is a object and not a function, is because technically scikit-learn is not really expecting us to use this. They have built into scikit-learn a function called plot confusion matrix, which essentially combines these two into one operation. However, because scikit-learn is a different machine learning library, plot confusion matrix relies on you actually passing it a model, a scikit-learn model, but we have TensorFlow models. So it doesn't work, essentially, the normal plot function. So we can just kind of rebuild it this way, which isn't too hard. Cool. Awesome. So there we are. Now we can jump down to our evaluate function. There's our confusion matrix stored. So this confusion matrix display object we can construct as, I don't know, I'll call it, because it'll be a plot, so plot like that. And we give it, remember when you're constructing an object, you start with the name of the class. So there's a confusion matrix display, and this here takes a couple of arguments. The first of which is the confusion matrix. Or actually, I guess these can be in any order you'd like, since they're keyword ones. So first we'll give it the confusion matrix. Well, not quite the function, the equal sign. And here is CF. That's where we've stored it. Hello, spider. Please stop blocking my way. Okay, cool. There we are. Confusion matrix. And the other thing that we'll pass it is our labels, because we would kind of like these to be not just gestures, 1, 2, 3, up through 7, but we can give them some names. So I have prepared, or I put in the oven beforehand, or whatever the cooking show thing is, or I guess here's one I made earlier. Et voila! There's names for our gestures. They're shortened acronym versions. So like clench fist has become CF. The Spider-Man is just SM. Thumb to pinky is T2P. So kind of like that. So this at least gives us a semi-human way of thinking about these. You could also give them full names. It just doesn't look as nice in a graph because like they're long sometimes because I was uncreative in naming them. So there we are. There's our gestured labels, if you will. So the other argument then to this confusion matrix display is exactly that. Display labels. These display labels are going to be, I think I called the function gestures. Yeah, lovely. Or variable gestures, sorry. Wonderful. Cool. Once we're there, we just need to plot it. So you can do that by doing the CF, or sorry, I don't know why I've done CF everywhere. Oh, I must be thinking confusion. Let's change that to CM for confusion matrix, since that's what it is. Don't really know how I've managed to pull that off, my bad. That's the second time today I've done that as well. There we are, confusion matrix, CF, or CM. Oh, did it when I was speaking. Cool. Anyways, the confusion matrix plot here, we want to actually plot. And you can do that by typing .plot, so that'll show it on the screen, or in our case, up in this little plots place for spider. So we'll go ahead and run that. Of course, it'll do nothing, sorry, because I haven't run evaluate. If I run evaluate, it'll think about it, and up here in the plots pane, wow, it's a confusion matrix. That's kind of cool. Let's make that a bit bigger so you can actually see what's going on there. Cool. So this looks just like our other matrix we saw a second ago, except now this time it is graphical, and it even does some color coding for us. So things that happen a lot are this more yellowy color. Things that never happen are this purpley color. So the true label, so things that are, for example, truly supposed to be a Spider-Man gesture, are sometimes getting mixed up with a clench fist gesture. And if you think about it like in a physical perspective, the difference between clenching your fist and clenching your fist with two of your fingers is not massively different. So maybe that's why it's confused between those two categories, we can assume. Here, wrist side-to-side vertical is getting confused with wrist side-to-side horizontal. If I'm honest, I think that's because they're almost identical gestures. So one of them is like this, wriggling your wrist with your hand straight vertically. The other one is doing it side to side. That one makes sense to me as well. It's kind of remarkable that it's gotten it right as often as it has. Well, I say that. It's only gotten it right half the time with this data. Let's take a look actually at all of our data. So this is just our testing data. If we take a look at, I think all of our data, the inputs were called EMG data. Well, we can check over here. EMG tensor even, and labels is the second one. So EMG tensor and labels. Thinking, there we are. Yeah, so you can see it does better on the training data overall. Oh, another reason it might not be as good here is because there were only 21 repeats of this data. You might be wondering, Brooks, why are there only 21 repeats of this one when you promised me there were 30 of everything? I might have mentioned it before, but Thomas was our guinea pig for collecting all of this data. We were both counting. He got to 20 gestures, or 21 even, and said, I think that's 30. And I said, I don't think that's 30. And he said, I'm sure that's 30. And then I was right. It was 21, but oh well. It's still enough for the model to figure out most of the time. But maybe that's perhaps more a lesson about when you're collecting data. Be sure that you have a good data collection method instead of just, winging it like we did. So maybe bring a counter or write a piece of software that actually just does it better than whatever janky thing we were using. Lovely. That's what a confusion matrix looks like. I'm trying to think if there's anything else that's worth showing off there. Sometimes, I guess, this is more just a plotting thing and less specific to confusion matrices. When you're plotting things sometimes, you might find that these bottom labels are really long and overlap with each other. In this case, that they aren't, but if I made this one really long, reran that. Whoa, it's on top of my other labels. I guess, sorry, that's probably a bit small. But you can see it kind of overflows. That's horrendously ugly, and obviously entirely illegible. So if you want to fix that, this is actually with a plotting library we're going to look at a bit more like today. It uses it in the background, matplotlib. But you can do X ticks. So those are the little tick labels down here, and you can rotate them. So rotation equals, and in this case I want to do 45 degrees. So I'll put them all in a nice diagonal so they don't overlap with each other. Theoretically. There we are. Now you can see, really gross still for being so long, but at least isn't overflowing and running on top of any of the other labels. So that's a nice little tip. Cool. I will also fix that so it's no longer terrible. That was pretty terrible in itself. There we are. Nice. Okay. Cool. That's confusion matrices. We can also change our function if we want to give us a little bit more information when it's evaluating it. We can ask it for the overall accuracy of the data that we fed it in. So for that, what we can do is just different ways to do it. We'll do it the simple way, which is to use model evaluate, which we have seen before. So after we plotted that, we'll do model.evaluate, and we want to put in our x data, get out the y data. And this will return a percentage of how accurate it is. So just to show that off with return, like this. Lovely. Voila. You can see it's outputted two numbers even, actually. These two numbers are the loss as the first number, the accuracy as the second number. We are interested in just the accuracy in this particular case. Also, it's, as you can see, printed its own thing here, which I'm not too terribly keen on since we'll be outputting that in a nicer way anyways, so I'll probably get rid of that. So to get rid of the output, you can say verbose. That's how much output it prints. You can increase this or decrease this, but I'm going to decrease it. So 0 is the lowest level. That means don't print anything. And then we want just the accuracy number. So that's the item at index 1 because it's 0, 1. So if we go ahead and return this, you can see it'll just be the accuracy percentage now. Well, not quite a percentage yet. There you are. You can see our output, 96%. Repeating. That's bizarre. Very neat. Okay. Cool. And then from there, we want it as a percentage. So, and we also want it printed. So I'll just do print. And we'll multiply it by 100. Make it a percent. Here we're going to use my favorite things again, which are format strings, the little f strings. So put an f before it. And I'm going to say the accuracy. And then anything that you put in the curly braces inside of here, remember, is run as code. So I'll do that, and you multiply it by 100 in that code, and then put a percent sign at the end. And then it'll spit out, well, when I run it. There we are, accuracy. You can also see, that's a lot of decimal points. That's kind of ugly and useless. I would agree. You can limit how many it displays as well. I think I showed this, maybe I showed this last time around. Yeah, in format strings, you can do a little colon here, and then dot, however many decimal places you want. So 2 decimal places, why not? And then toss in an F for floating point formatting. So this combination of thing means give me 2 decimals on floating point numbers. And if we go ahead and run that, there we are. Much nicer looking. It's even done the rounding correctly for us. Very polite. Thank you, format. Cool. That is that, I think, for our evaluate function. We get a confusion matrix out of it every time, and then also this. So, in fact, I'll nuke that. And we'll go ahead and run it for our... Oh, Spider is displeased by my decision to close that. We'll see if that comes back to life. In the meantime, any questions about the evaluate thing that we've done so far? I'll just create a little poll. How are people feeling about confusion matrices and accuracy calculation, I guess. Accuracy calculation. I just realized those don't need to be nearly as long as they are every time I write them, because theoretically, if you're answering these polls, you can hear me talking to you. Hey, good morning, Spider. Welcome back. It was good timing. Hey, and people are feeling good about it as well. Yeah, confusion matrices are really cool. I like them a lot. And now we have them. I will, if it is all right with you lot, keep our whole prediction section down there still commented, but I'll uncomment our part where we're training the model, and instead of doing this typical evaluate at the end, I'm going to do our evaluate. So I guess we've kept lots of those names the same, so toss here at the beginning, evaluate function, give it 3 parameters, the model, the x-test, and the y-test data. Go ahead and run that whole thing as a group. It'll go through, it takes a second because it's loading TensorFlow for the first time. Go ahead and train the model. Dun, 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 dun. Gives us an accuracy and plots our confusion matrix all in one go. Very nice, I think. And you can see obviously the confusion matrix changes every time you look at the data, because it's training differently each time. Wonderful. Cool. And it was 96% accurate that time. Well done, Mr. Neural Network. Cool. So that is that. People seem to be feeling good about it as well, so that's fantastic. So I suppose the next thing to move on to, earlier I hinted at it, but we'll do that after the next thing. So the next thing instead will be, when we're training these things, well, like I did just say actually, each time we run this code, it will give us a, well, semi-random result. So that one's 96.5% accurate, we'll remember that. This one is going to be 98% accurate, so even better. Well done, model. I'm going to change this actually back to a convolutional model just because they train faster, so I can do these rerun things faster. So 98.2 versus 98.2 again. Very well done, Mr. Neural Network. 100% that time. 96% that time. TensorFlow is now whining about me calling things in an order it doesn't like. Fine then, TensorFlow. I won't print the model summary. There we are, back to our 98.2. So you can see it kind of bounces around a bit. Our confusion matrix is up here. They're moving, they're changing, so we can actually go forward and backwards with these. So even though we're just running the same model and over and over again, they have different errors, kind of random. How do you decide which models are better than the other when it could just be down to random chance? So that's what we'll do next. The answer is using statistics. How fun. But for statistics to work, you need to do these things over and over again, like we've just done, where you repeat it, that process. So the thing that we'll do next, then, is we are going to look at, essentially, training our network over and over and over again in a sort of loop, and then collecting all the data from every single training, and then comparing that, and seeing which one is, in the end, better than the other. So I think, for that, we're going to want a new function. We can call this one train model, because that is what it will do. Train a model. Cool. What will this take? This will take a model that hasn't been trained yet, and it will then take some X data and some Y data and some optional arguments I'll toss in there for us to tweak. Is number of repeats. So this is how many times we're going to be repeating the full training. So that will give us different, well, I guess, answers for how well it, well, that'll help us be more certain about the output. And then here for epochs, well, that is what it says on the tin. That's this number, the epoch number. So we might want to change that, say, if we're doing a convolutional network versus an Lstm or something like that. Whoops. Let's set that to 30 even, just as a nice default. Kind of in between where the Lstm was fully trained and where it was a second ago. Cool. Nice. So within this train model function, we have to think about some of the data that we want to keep, I guess, as we go along. And also the data, the data that we want to get out of it, essentially. I would like, out the other end of this function, a list of how all of the trainings went. So basically, how did the training progress over time? How did the loss decrease? How did the accuracy increase over time? I'd like that data. And I would also like to know how long it takes to train each one of these things, because time is a kind of important factor sometimes. And we could see it pretty easily when we're running our code, like it just takes longer or doesn't take as long. But we don't have any number output from like TensorFlow saying this model took this long to train. It just gives us per step, not necessarily for the whole model. So we can calculate that as well and return that. And I think that's what I want at the other end. And also we'll have it return the fully trained model. That makes sense as well. Cool. So what we want to do here is first create some new arrays. You probably actually don't see me creating empty arrays too much and appending to them in my code. That's because I always prefer list comprehensions when I can use them. However, in this particular case, the code that would go inside of the list comprehension is kind of comically large, and it looks, well, for a list comprehension, so it looks a bit better as a for loop that we're appending things to. So that's what we will do. Lovely, and then times here. So this will store the list of, you know what, I think I'm going to call that histories. That's going to return the training histories. This is going to return how long it took for each one of those. So you know what, training time, training hist. Use good variable names. It saves you the time that I just had to spend explaining what they were. Okay, love you, lovely, love you, love you all anyways. Cool. Then what we want to do is go through for some number of repeats in a nice for loop. Do I care about recording the repeat number? Yes, I do, because we can print that as output on the console. So I can do for repeat in, and this is just a range. So we're going back to our basics here in Python, where you can generate ranges from some upper number. So remember, if I do range of 15, which in this case will just be range repeats, since we took that. Remember, that will be a nice list. Well, it won't be a list by default because Python would be a bully and say it's a range object. If we just go ahead and turn it into a list, however, we can see that it is indeed all of the numbers between 0 and, well, it's exclusive on the upper end, so all the numbers between 0 and 14. Importantly for us, this list is the correct length, which is 15 long. So that means they'll go through this loop 15 times, and we're asking for 15 repeats, and it'll record which repeat is on at any given time. Cool, lovely, we have a loop. Now what we want to do in here, when we're training our data, remember the first part of training our data is actually splitting up the data like this. So we could give our neural network the exact same splitting of data every time, but that might actually not be very realistic. Well, because when we're rerunning this file, for example, it's getting a different split of the data. And also, we'd probably get, well, almost the same behavior every time if we gave it all the same conditions every time. So this test train split, I think I might have told you before when we were talking about it in the last session, it does a lot of randomization for us. So it first shuffles all of the data. So all of our repeats come in a random order, but it shuffles them like equally for the x and the y, so it still keeps them like related to each other. And then it also splits them into the testing and the training data by default 75%. So you can see there's 58 in the testing data. That's the smaller set, 75% of it sitting in the training data. But each one of these things, for example, which repeat ends up in the test and which ends up in the training thing, that's random. So we'll want to repeat that every time we're doing our training. So in fact, because I'll be replacing all that training down there with it, I'll do a cut. Goodbye, my friend. There we are. Test train split. We're doing that now on our loop. So we're going to do it 15 separate times. Since we want to time our training, it's worth showing you how you can time things in Python. There are a lot of different ways. This way is probably not even necessarily the best way, but it's certainly the simplest way for what we're doing. We'll import the time module. This one is built into Python, which is good. Will you give me any help? Hey, look at that. Yeah, so you can go and look through the whole, well, not the whole thing, but just the documentation for the time module. So if you want to do things with time, that's the Python library that's got you covered, or module. It's built into Python. And what we're going to do is get to the time, and we're going to use a particular method called monotonic. So if I do time.monotonic, you can see what it looks like. What monotonic means is it's always like, of course, because I haven't imported time. That's not how you spell time. There we are. That's all. Ooh. There we are. So, wow, that's a number. And that's kind of the point. Time monotonic doesn't really give you something terribly directly meaningful, but what time monotonic is guaranteed to be is always increasing. So that should be trivial. Time is always moving forward, not backwards, right? Well, unfortunately, computer science forces you to deal with every single of the exceptions to that rule. So for example, imagine you've just got a flight and you've flown to a time zone where it's the same day, but it's earlier in the day. I guess that might not, yeah, that can happen, I guess. At least, so when your like computer gets updated with the new time zone, it looks like time has jumped backwards. Or maybe the thing that's coming up, maybe this weekend, I forget, daylight savings time, or one of the two. Either, well, British summertime, I guess, would be, yeah, going back to British summertime. That would change the clock. What monotonic says is, okay, I'll worry about that complexity for you. You don't worry about it. Just know that if you call this function a second time, the number will always be bigger, I promise. And that's true in this case as well. And I believe this is giving it, yeah, this is giving us actually the value in seconds. This is maybe seconds into the day, maybe seconds since I turned on my computer. Both of these are equally possible. I'd have to check and see exactly what it wants out of you, or wants out of us. But the important part is to remember this gives you seconds, and it's always increasing, and it's the amount of time that like your computer has experienced, not time on the clock. Lovely. So, and that we can use to record our start time, because if we want to know how long something took, we can just get the start time and the end time and calculate the difference between the two. So that's what we will do. We'll do time monotonic. Wonderful. Then we want to train our model, so we know how to do that. I'm going to do something. Yeah, it's fine. We'll do this first. Model fit, and we want to train the model with the x data. Well, actually, no, not here, because we've done this we've done the test train split. So we do actually now have test and train to use again. So we want to train it on just the training data. So y train and x train and y train. Lovely. Those are all fit. And then we want to do it for some number of epochs. In our case, we're just going to set that the same as our argument up here. Try spelling that correctly. Epochs. So that'll be 30 by default, or whatever else we give it. And then also we're going to turn off the output for this as well. So verbose equal to 0, just like before. So we're going to hide that, replace it with our own print message. So it's a bit prettier. Cool. Once the training is done, we do end and get the time there. Time monotonic. And it's going to tell us the ending time. So start time and the ending time we can then subtract to get our total time passed. So we'll do those are both several things. So I'll do plural training times. And we're going to append to that list. Whew. I am half asleep today, I swear. See, I can't speak properly. I can't append properly. There we are. Lovely. End time minus the starting time. That's how much time has passed. I'm going to temporarily actually ignore the training history, so I'll show you that in a second. What's your gripe there? That's because I've called it start time. Let's just call that start, because that's what I've done here at the very end. Cool. And we'll print how long it takes, I guess. Yeah, and we'll add to this as we go. So currently, what we can do, an f string again, we'll say what repeat it is. So this is repeat, and then here we can have the numbers. So this is repeat, well, we're storing that as our for loop variable. In fact, we probably want to do +1, I think, since our first repeat should be our first repeat, because humans like to deal with 1 indexing instead of 0. And then that is out of how many repeats overall? Well, that's our repeats variable. Repeats. So that'll tell us how many we've done so far. And then we'll also say time. Yeah, we'll just do time to keep it simple. And that should give us seconds, I believe, which will be nice to just print directly. So we could do the... do I want to recalculate that? No, it's just that that's, yeah, it's pretty long, but that's fine. So we can do training times. And then we just want the last thing. So remember, -1 indexing means you're indexing from the right inwards. So -1 is the first, or sorry, the last item in a list. So if I did 1, 2, 3, 4, 5, and then I wanted the thing at position 0 or position -1, that'll be the last item, which is 5 here. So it's going to give us the most recent time. Each time it prints this, then it's going to repeat the loop, and then once it's done, I'll have it return the model and also the training times. Like that. Lovely. And we'll add in the whole history thing in a second. Excellent. Train is not defined. Of course it's not. Yes, because this I have destroyed. Yes, so you can go away. Goodbye, my friend. And I will replace you with train model. And here, our model, yep, that part's fine. X and Y data. Here we're going to give it all of the data, because remember, it's doing the splitting for us. We want to give it EMG, tensor, and labels. So now the data we're giving it here lines up with the data we're using to build the shape of the convolutional neural network. Cool. Evaluate. Right, of course. Well, looks like you're just going to evaluate the whole model, aren't you? Just for the time being. We can always fix that later. Tensor and labels. Cool. Go ahead and run this. There we are. Repeat 1, 2, 15, and it's telling us, so we got 1.5 seconds for the first one, then we're dropping down to 1.3. Now, well, to my eyes, that looks hideous with that many decimal points. Does anyone remember how many, or how we can calculate, did that return anything? Oh, I didn't save it anywhere, so I wouldn't know. How we can display that with fewer decimal points. Does anyone remember how we do that with f strings? Dun, 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 dun. Spoiler alert, the answer is elsewhere on the same screen. Any idea? If I want to show 1 decimal point, or maybe 2, whatever you're feeling. First one to give the answer decides how many decimal points we show. Wonderful. Yes, okay. So you do that. You do have to put it after a colon, so you separate the things that you want to print and the options for printing it with a colon in F strings. That's only inside of these brackets here, because obviously these colons outside of the curly braces don't have any special meaning. They're just in the string. So here I can do dot 1, as was suggested, for 1 decimal place. I think that looks good. I'll also put after it S for seconds, so we know the unit at least. Now when we run it, it'll be nice and pretty. There you are. First one took 1.6 seconds versus 1.4. And it'll tell us all that. Lovely. So that's really nice and helpful. And also, the thing that it should be doing, that we are not actually getting out the other end of it, is all the things that it's updated. So the model, it's returning as its first argument. Well, first thing it's returning here in this tuple. The second thing it's returning is the training times. So I'll just shorten that to times. Yeah, that's fine. Okay, and I'll run that. Oh, yes, I forgot that takes a little while, doesn't it? Turns out 1.5 seconds is really fast, but it's much less fast when it's 1.5 seconds 15 times. It is, in fact, 15 times slower. Who would have thought? Okay, so that'll spit out something in just a second, and we'll be able to take a look at our output. Lovely. Okay, our variable explorer has been updated. We have, first of all, the model, which is now entrained. Well, that's never shown up there for some reason, but the model here, of course, is there. That's trained. And here, times is now a list. Lovely. And you can see it still keeps, of course, the full value, or the full, like, you know, decimal place precision of these numbers, even if we print it with just 1, because the printing is just for show. It doesn't actually change the value that you are printing. So, lovely. There we are. We can see all of those times. There are 15 of them. 14 is the last one. 0 is the first one. Great. So, if we want to get some information out of that, we could like average it or do a standard deviation, but we'll do that in a second. First, we're going to get training histories sorted. So this is something you probably haven't seen before, which is kind of cool. Trying to think about the best way to do this. Yeah, that's a nice way to do it. So model fit returns a training history, which is a special object. So we'll print the history, and just to stop the loop from, well, I was thinking about to stop the loop from looping. We can also just set the argument to 1 repeat. That's the whole point of including that as an argument. So I can do repeats equals 1. Lovely, and we're gonna run that. And we'll get out that time, and you can see here it's printed this history object. Wow, that's very unhelpful, you may say. I would agree. Luckily, this object's nothing too mysterious. You have to look in the documentation for it, or just you'll know now. For some reason, despite being a history object, you have to do .history to actually get the history out of it. Just because that's history is only one of the many fields it includes, it looks like. So here you can see, here's our history object. We have 2 things in a dictionary. That's a bit hard to see, actually, maybe. But it's a dictionary because it's got curly braces. First thing is loss, and it's got a big list here for us, and that list goes until there. And then the second thing you have is accuracy, and that's a big list here. Same amount of things, but with some, I guess, nicer looking numbers, so that doesn't look as visually as long. I think it'd be nice to know the accuracy as our model is training as we're going along. So let's print that even. To do that, we can just jump over here to our lovely little string. I'm going to put accuracy in the middle even. So I'm going to do accuracy. And now we have to compute it to put it there. So this history, I want to actually just store that in our training hists data. I think that'll be nice to have there. Training hists, not hits, hists. There we are. I have to update this down here. I'll just make it hists. There we are. Lovely. And now, where we're appending to our training data, we also want to append the accuracy. But we're kind of only interested in the final accuracy. We don't want the full history when we're printing it out here. So we can do that pretty easily. We can go, doesn't really matter the order. I'll do training hists, and we want to append to that. And appending to this, we're going to append hist.history. Lovely. Get rid of our printing boy. Bye-bye. And that's what we want there. Wonderful. And our accuracy, if we want to get the accuracy out of that history, first we need to look at the accuracy part of the dictionary. So if you recall how to... it's going to be really gross and long. Is that fine? It is certifiably kind of annoying. So, well, we'll put it here anyways. It's fine. It's only happening once. Cool. So here we'll put, same as we've done for our time, where we look at training, this time hists. We want the last thing in history, so -1. But we don't want to print everything there. We just want the accuracy. So that's where we tack on our accuracy. Okay, I made the executive decision that's too annoying to all put in the string, especially because it's got quotes in it. So we'll move it into its own function. So we'll say final accuracy is equal to that, and it's accuracy. And then it's the final thing in the accuracy list, which is, again, -1. So that's a bit gross, right? But it's fine. Cool. That'll do. And then in here, we just put our final accuracy. And I'm also going to do that as a percentage. So I'm going to multiply that by 100 and format it to be a percentage with 2 decimal points. Why not? And we can go ahead and run that. Hey, lovely. Actually, 100% after that? I don't believe you. Fascinating. Well, let's run that with some more repeats and see what's being squirrely. Maybe it's because the model is already being trained, or already been trained. So we'll get rid of that. Move us back to 15 repeats. Go ahead and run that. That is incredibly suspicious. I assume that has to be because it's using the old model, but that's really confusing because it looks like it's rebuilding the model there. That, or we've just done a calculation incorrectly. So let's find out together. I'm going to delete the model. Goodbye, model. Okay. And just to double check, it does not exist. So if I try and train it, you will not let me train it because it does not exist, right? All right. So if I go ahead and build the model, then we will build the model. Then we'll try and train it. And it will continue to behave incredibly strangely. Okay, very odd. So I feel like that's an error on my part. So let's take a look at what final acc is. Cool. Accuracy. So there we go. We'll print our final accuracy, which I assume must be just 1 every time if it's giving us that, which is very much not correct. So we'll also look at that. In fact, let's just look at all of training hists and see if this checks out. So I should have actually here hists as a variable, which is legitimately 1 for all of the accuracy. That is fascinating. But the loss is started so small that that's obviously not training from scratch, which is very, very strange. And I'm not sure why it's gotten up to doing that. Oh, just kidding. I know exactly why it's doing that. I'm the reason it's doing that. Sorry, I removed part of my code when I was typing this in because I wanted it to be a learning lesson later, and evidently I've already forgotten enough and I've been refreshed on my learning lesson. So let's go ahead and run this just from a totally clean terminal, and you can take a look at it. Again, it should start at less than 100% accuracy, so that part is properly, like, strange to me. But at least this time we'll know this is the first time it's been run. But I'm not saving it anywhere, am I? I am. I'm saving it in hists. So we'll take a look at hists and we'll see what's going on. Sorry for the squirrely behavior here. Right, okay. So hists a list of different histories. Of course, the final model, that's why that's fine. The final model has got a full accuracy, but what about the first one is the question. How is that one training? Oh, just kidding. Also, this is probably fine from the get-go in general. The reason all of those are ones are because it's on the training data, and we're only seeing the last number. Sorry, I'm being silly. I've just not written this exact code before. So you can see on our first one, it's starting here at a lower percentage, and it's working its way up, eventually to be 100% accurate on the training data. We could also give it the testing data if we want to evaluate it on that. I'm thinking if that's worth doing. Now we'll do that in a minute. Cool. So you can see for this first entry, it's actually training the model, which is great, fantastic. The loss gets down to be pretty small. What is less fantastic is the fact that our second model here starts at 100% accurate, which is not indeed correct. So the reason this has happened is because we have not reset our model since we last trained it in this loop. There are probably a few different ways to reset a model, but one way that you can do that is just by storing all of the weights of it. So the weights are essentially the values of all the little parameters at the very beginning. So we'll go ahead and take a look at that. So we'll have our y. No, sorry, not that. We want to store the initial weights. So we'll do that here. To get the initial weights of the model, you just do .get weights. And notice we're doing this here before we are training the model. So we'll have those stored beforehand. And then what we do is each time we go through this loop, we're just going to take, what should we do it after? We definitely want to do it before, otherwise we'll wipe the model's training progress if we do it at the end. So we'll do model, set weights, and then init weights. So what this will do is at the beginning of each loop, it'll reset the training progress of each one of the things, so it has to be trained back from scratch again. That's the bit we left out. So if we go ahead and do this, lots of them being 100% accurate because it's just the training data. We could actually probably reduce the number of epochs and it would be less accurate, I reckon. Yeah, let's give that a go. That'll give us some more interesting results. Repeats. Yep, and it's our evaluated diff on the testing data is 99% accurate, so pretty close to the 100% that it's being trained to. If we do something really terrible, like only, oh, not repeats, epochs even. If we train it really quickly with just 5 epochs, 3 epochs. Yeah, there you are. You can see things are much less accurate. Okay, so it is functioning correctly. It's just that beforehand, it was getting to the 100% accuracy on our training data, which it will usually always do after some amount of time. So we'll set that back up to like 15, for example, let's say. Because 15, I think, gets us pretty close to all the way there. Or maybe all the way there every time, but it's just faster. Wonderful. Cool. Okay. Now, from the data that's returning, this history data, we can plot it. I'm going to have to go a little bit fast on this last bit because, once again, things have overflown slightly, but that's okay. So you can see here now, all of our history things, they start not trained, but then they become trained, which is really nice. And it would be nice, I think, to plot all of that, that training progress for all 15 of them. So for that, we'll create a new function really quick. I'm going to fly through it a little bit quickly. Yeah, that'll be fine. Plot training. And here, what are we going to grab? We're going to grab the histories. And from the histories, we're going to plot something. I'm trying to think. Yeah, it'd be nice to be able to plot different metrics. So let's plot by default the accuracy metric. Accuracy. Lovely. There we are. And here, now we're going to have to import something called matplotlib. So this is something you can use to make plots in Python. You may have come across it if you've done like any other basic Python stuff before. I know that the uni course that they have in the comp sci department has some bit where you're doing matplotlib. PyPlot, that's the one that we want. And we're going to import that as PLT, just to shorten the name. And down here, we're just going to, thinking about the order I should do this in, let's start with the actual important part. Yeah, so we'll just take a for loop for all of our histories. And we will go through all of our histories one at a time. So actually, it's going to so for an individual history from the histories. So, oh, that keyboard shortcut did not work. For hist in hists, it's going to give us one of the plotting histories, and then we're going to put it onto a plot with lt plot. So this is similar to what we saw when we were doing our confusion matrix .plot, except now we actually have to give it data to plot, and the data that we want to plot is going to be history, and in this case I want, well, whatever the metric is. So in this case it'll be accuracy. So we'll go through and make all those on a plot. Let's see how well that works. In fact, I should put that after here, but we can put that there in a second. So there we are, it's trained. Ooh, that time it didn't get to 100% quite. So now if I go ahead and do plot training, and then we give it our hists, hopefully that'll pop up plot. Hey, look at that, very nice. You can see this training diagram. So this is our accuracy there, and this is our epochs, and you can see it's increasing as we go along. Fantastic, and even converging up there on a 0 eventually, which is really good. Or on a 100% accurate, which is really good. Now, with that being said, it'd be nice if that had, you know, labels, right? So we can do that. And do I care about the size of it? No, because that'll resize automatically, that's fine. So we can do plot, and we can add an X label. So that's just the X axis label, and that one is going to be epochs. And then the Y label is going to be loss. So actually, let's try before I rerun this. Let's try taking a look at the loss metric, or well, sorry, that's going to be whatever our metric is that we're looking at it. So here is accuracy. If we change the metric to be loss, so remember this should always be decreasing because loss is like the error in the network. So there we are. That one decreases. Lovely, wonderful. Obviously, though, our label will need to change depending on which metric we're using. It would be nice if our metric were properly capitalized. Magically, Python has a method for that even. So if I take our lowercase loss there, do dot title, that'll turn any string into title case, uppercases it for me, which is very nice. So here, that means I can just do metric dot title, and that will capitalize it. So if we run this, whoops, forgot to add it down here. Yeah, it's probably good to put before the evaluation, I reckon. Plot training. Ooh, cool, yeah, it's of course giving us a confusion matrix again, and yeah, and I'll just run the thing here instead of typing it out there. I'll type it out there in a second. And if we plot the training for loss, you can see we get this, with loss over here, epochs over there. I think that font is a little bit small, so we can improve that as well. If we do plot RC is just like a list of different like keys for a bunch of different things. In this case, I'm interested in the font. So for the fonts, I want just to make the size 24, which is a bit bigger. And I'll also finish doing plot training down here. In fact, I can plot both of these. I can plot both the loss and the accuracy. Lovely, and we are bumping up right against time. So there's our accuracy. So go ahead and run this. And it will go on through, do some training pretty quickly, which is real nice. And it will plop back out some answers for us. Lovely. So there we are. We can see up here, this is loss, and that's going down, and you can see accuracy. Intriguingly, it's printed loss small and accuracy large. Not certain on why it's done that, but that's all right. And it's also put a line on there that's a bit strange. Maybe I'll rerun that just to see if that's repeated strange activity. In the meantime, though, since we're just about at time, the further things that you could do with this, which I guess we haven't quite gotten time to do today, but are arguably, I guess, the simpler parts of the process. Oh, it's just only plotting one of them. Ah, of course, and it's showing loss down there on a separate thing. Yes, okay. There we are. That's a good lesson to teach people. You might have noticed I'm calling plot here in a loop. And what that's done is put both the loss and the accuracy on the same plot. So actually loss is up here. That's the really big number. Accuracy is those really tiny lines. That's kind of useless. We want them on separate plots. At the end of plot training, we should do plot show, I believe it is. And that will show a plot as a separate plot. This will separate them out. That was me being silly. Sorry about that. Yeah, so anyways, as I was saying, we've kind of run out of time, but that's all right, because the bits left to do, for example, if you, yeah, that's much nicer. One of the compare things are, when you're looking at your machine learning model, if you want to check if, am I using enough epochs, you can check out something like the accuracy or the loss thing, and you can see, well, okay, after about 8 epochs even, it's doing pretty well. And you can check over here, 8 epochs doing pretty well. So you could just stop it after 8 epochs. So this helps you tell if you're training for too long or too short of a time. Confusion matrix tells you which particular things you're mixing up. See, look at that 21. It's Thomas's fault, not 30. So I'll tell you which things you're mixing up. So maybe you can think about if there's a reason that might be. And then what you could also do with what we've recorded here in our hists, you could go through, you could calculate the final accuracy of all these different models on, for example, the training data with this evaluate. So you could run our evaluate after everything to get the accuracy on the testing data, and you could calculate the average accuracy of different models. And that was the only bit that we didn't have time necessarily for today. But you could imagine just running this for each one of these models to get its average accuracy. And then with that, on the testing data, and then with that you could calculate, aha, this model is actually better than the other model, because you'd at that point have been running it 15 times over or even 100 times over, and you've gotten a big, nice, statistically significant average number. So that's how you can kind of play around with all of that. I realize it is slightly past time, and so I will do 2 things for you. First of all, I will kick your direction a quite apt little feedback form for today's session, in which you can roast me for moving, well, apparently not quickly enough, for moving not efficiently enough, I suppose. And I will also take any questions that people have. So I will ask for, I'll do a little poll for any final questions, and feel free to type questions in either place. Yeah, sorry, I've been kind of scatterbrained today. I think I've become quite hungry and tired. I pulled an all-nighter yesterday for an essay, so that's why I'm like shattered. I apologize. Awesome, okay. I may have confused someone. Somebody's put a thumbs up for any final questions. Does that mean you do have a final question? Or if you put a thumbs up because I tricked you and made this one a negative answer, is the I don't have anything to say one? If you do have a final question, feel free to ask it. Yeah, lovely. Nice. Otherwise, yeah, I'm around if anyone does have questions. If people don't, then I will see you next week. If people are interested when I write this one up, which I'll be honest with you might not be until Easter holiday, but I'll send out the recording tonight. But once I write this one up, I'll include the part where I'm actually calculating the average accuracy, and you'll be able to see that as well, which should be really nice. And I'll ping you all when that's up. I'll probably mid-Easter holiday. But aside from that, next week then we'll probably be shifting gears a little bit away from machine learning-y things and towards designing PCBs in electronics, which is a kind of cool process, which I learned a bit about last year. So, awesome. Yes, what is plot_rc doing? Fantastic question. Yes, so what that plot_rc question does, or question, rather, method, RC is kind of like, well, you know what, let's find out what RC stands for together. It's just like general resources, or like information. What it's doing for us is it's made our font bigger. In this particular case, because I've taken the font group of settings and I've set the size of the font to be 24, but you can set all sorts of options for this. So let's take a look at its documentation. So that is in pyplot, and pyplot has RC in it. And here you can see, et voila, documentation. So you can set a bunch of different things. For example, for lines, you could set their width, their style, their color. For fonts here, you can set the family of the font, the weight of the font, the size of the font, and you can do all of that. So it's just a way of setting different options. I wish they would tell me what RC param stood for, because obviously that's an acronym, but they don't want to share. So, well, hey, look at that. There's a Stack Overflow question on it. The answer is It's a historical reason. The reason is because historically, lots of things have been named configuration files as being RC for being run at startup, and then they configure your things. So running configuration. Yeah, historical reason. But does that answer the question of at least what it's doing? It's letting you set options for your plotting. So we could set like colors there or font size in our case. Awesome, cool. Are there any other questions? And this can be like anything machine learning, because this is technically speaking our last session on machine learning as part of this bootcamp, I guess, set of things. But if there aren't any final questions, feel free to head off and have a lovely day. If there are, I'll stick around until everyone else is gone. But thanks for coming to these, and I will see you all next week for some PCB making. Well, designing digitally, I guess, anyways. Cool. Lovely. I'm glad it was good, even if it was a bit of a mess today. Happy to help a little bit, though. Yeah. If questions come up as you're doing things in the future, feel free to annoy me on the Discord, and I should be out. Cool. Awesome. Any questions from either of you guys? Awesome. Happy to help. Glad you enjoyed it. Awesome. Thanks. Yeah, thanks for coming. Cool. Any questions on your end, or perhaps you're away from your computer at the moment? It's hard to tell. Cool. I will assume you are away, so I may have to depart. But oh, no worries at all. Any final questions about machine learning things? Yeah, I'm right. This is the last session on the machine learning stuff. Awesome. Cool. Happy to help. Coolio. Yeah, in that case, I will see you next week. Oh, goodbye. Oh, record.